Welcome, everybody, to the American Space Museum. I'm Marquette, and we're so glad you're with us to stay curious today. We have beside me Dr. Eric Pearlman from Florida Institute of Technology, an astronomer who has time booked on the Webb Telescope. He's worked on the Hubble, all the major observatories. Thank you for coming here on this important day of astronomy.
Thank you, Mark.
In history, right?
Thank you for having me.
You're welcome. So you got a big smile on your face. How many interviews have you done today about the Webb Earth flight?
I've done 3. This is number 4.
Good. Well, excited, obviously.
Oh, yeah.
And what's it like when mainstream Joe and Jane America and the whole world get into astronomy?
It's amazing. And I mean, it's the most fun part of my job to get the public interested in what I do. I mean, it sounds mundane, but it's not, because I like watching the light come on in people's minds, and I really like to tell people about what I do. And it's fun. It's really fun. And I mean, today I'm a kid in a candy store. I really am a kid in a candy store.
Well, here's one of the candy behind
That's
us here.
right.
Is
That's
the
right.
Karina Nebula that's very familiar to amateur astronomers, particularly in the lower latitudes and around the equator. This is an incredible image from Webb. They're calling it a mountain ridge of birth of stars in there.
Yep.
Dr. Pearlman, you're going to explain a little bit about it, and I'm going to read something about it here in a minute, because the poets are already working on these images here. But I want to set up that Dr. Eric Pearlman is an observational astrophysicist whose research concentrates on the nucleus or centers of galaxies. Why? Because that's where black holes are.
Right.
And you're a black hole expert, right? One of them out there.
That's right.
And but he has worked on the Hubble telescope, the Chandra X-ray telescope, other orbiting scopes. But really, the largest ground-based instrument in the world is CanariCam, and I looked that up, and that's an amazing facility. What country is that in?
So that is in Spain. It's in the Canary Islands. And yeah, CanariCam is one of the main instruments on the Gran Telescopio Canarias, which is the 10-meter telescope there, one of the largest telescopes in the world. And yeah, I was part of the science team for that.
Well, you came to FIT, which has grown, of course, leaps and bounds since you came in 2007, 15 years ago. And he spent time at the Space Telescope Science Institute in Baltimore, Maryland. That's in Johns Hopkins University campus. That is where the action is for you researchers of the space telescopes, whether it be Hubble and now the Webb telescope.
That's absolutely right.
And Dr. Pearlman, is kind of like a Merry Christmas to you amateur astronomers.
I know.
Why? Because Webb was launched on Christmas Day last year.
Yeah, and I mean, I'm Jewish, but I got up early on Christmas Day to watch the launch, and I mean, everything about it was just amazing. I mean, and the launch was fantastic, and the trajectory was even better than we thought it would be. They've got twice as much fuel as they thought they would have.
Yeah, the launch by the Ariane 5 rocket was so accurate that it didn't have to use fuel on the Webb to position it in this very special orbit. We'll see the pictures here in a minute.
Yeah, exactly right.
That. But we did want to mention that Eric was with us on Stay Curious on January 18th.
That's right.
Shortly after the launch. So 7 months later, wow.
That's right.
It flew by fast, or would you kind of...
So, it flew by fast in a way, but in another way, I mean, look, I was watching it. I was kind of on tenterhooks for each step along the way, right? Because each step along the way, okay, first this instrument is getting tested, and now the other instrument is getting tested, right? And the deployment, and 350 different ways that it could have failed.
On the internet, how they timelined everything, including 18 mirror segments, making up this 26-foot telescope.
And not to mention
21 feet. Sorry, 21.
Well,
feet.
right, but not only that, but not to mention the fact that they had to unfold this huge solar shield, the size of a tennis court, right? And then they have to unfold the telescope from that, and somehow not make the solar shield fracture, because that's an amazing thing about the Webb.
This purple thing here.
This purple thing, right? That solar shield. It's 5-6 sheets of mylar that it's thinner than the tinfoil you put on your sandwiches.
Right.
I mean, it is so fragile, and somehow it didn't break, right? And somehow, you know, the structure rebounded to be exactly where it needed to be, and they were able to get the focus even better than they thought they could get it. And then every single instrument, right? Every single instrument was right on.
And that's amazing. This is one of the most complicated things ever built. You better believe it, to operate away from humans. And gold-coated beryllium, mirror segments there, 273 square feet. You'd have 132 motors that behind them that all work. There's just an amazing engineering feat, really.
Absolutely.
The sun shield, by the way, keeps the sun, moon, and earth always behind this shield, because this telescope must operate at 370 degrees Fahrenheit below zero.
That's right.
223 Celsius minus that way. Otherwise, I'm reading here, infrared radiation from the telescope would overwhelm the instruments.
That's absolutely right. Yeah.
So this is a very it's just unbelievable. Northrop Grumman is the main contractor, Ball Aerospace, and L3 Harris, all businesses that operate in Melbourne, where your college is.
That's exactly right. And by the way, just to build on that, so that cold temperature, if you take a look at all of the images that were released earlier today, one of the things you notice is just how much there is in it, right? How much detail and how low that background is. If that telescope is not at 370 degrees below zero, that background is a lot higher. And guess what? You see a hell of a lot less.
And sort of what you call noise.
That's exactly right.
Pixelation in a way type of thing.
Yep, exactly.
Well, hope you're going to enjoy our program here with Dr. Eric Pearlman. We know that Perry Hall, Melissa Pope's probably watching. John Allman, thank you for your likes on our Facebook page. I'm pretty sure that we've got Christopher Mick is catching us today from Hudson, Wisconsin. And we definitely know Robert Law is enjoying a cocktail in Dundee, Scotland. Hey, Robert, one of our big fans. And Keith Soule.
Hey, save a gin and tonic for me.
All right. Marty Winkle, my cameraman and co-producers, redirecting the microphone here, as both Eric and I do have boisterous voices here. Good to see someone can speak up and stay curious here. Let's establish a little bit what you do there. This is just a graph that shows the 7 months of anticipation,
right,
and all sort of the check marks that had to go right on to reach this seminal point today.
That's exactly right. And I mean, you know, what that shows, and what I love about it is just, I mean, people don't know what goes on behind the scenes that first year in a mission. We're not twiddling our thumbs, right? There is a ton of stuff that is going on, and the checkout, the commissioning of every single bit of the telescope, every single instrument, each of that has thousands of different things that have to be done, and they have to be done exactly right. And so it's actually a very complicated and, you know, time critical operation. And there's a lot of things that can go wrong. And the only thing that's not shown in there is just how many of those steps were failure points where if it didn't work, things
You're
would come
done.
crashing down. You're done. Absolutely.
How many people are involved in this Webb project?
You know, I don't
Round
actually know
numbers.
the number.
Okay.
I don't. It's well over 10,000.
10,000.
I mean,
Okay.
yeah,
all
because
right.
if
Well,
because if you
I was going a couple hundred, a couple thousand.
a couple hundred just at STSCI.
In Baltimore.
Yeah,
headquarters.
right. But no, if you add those to all of the people at Goddard, to all of the hundreds and hundreds of engineers at Northrop Grumman, at Arianespace, at the Canadian Space Agency, all of their contractors, we're easily in the thousand. I'm betting it's over 10,000. I actually don't know the number, but I would be surprised if it wasn't over 10,000.
Well, before we get into showing you these images and Dr. Eric Pearlman comments on this $10 billion observatory, that was about 10 years behind schedule for various reasons.
Yep.
And then the pandemic, to get it done during the pandemic, you can't underestimate that, right? With
That's very true.
This very sensitive instrument to we don't want to put germs on and stuff like that. So the limited partnership with Canada, ESA, and America, and NASA.
You know, it's interesting that you mentioned that, because that was some of the it was the last stages of it, right? Because it's the last sort of 6 to 8 months of the run up to the launch, and then also physically getting the mirror on the mirror in the telescope onto the barge. I mean, there was a lot that had to be done during 2020 and 2021, and the pandemic definitely made it more difficult. And
yeah, well,
it's hard to get that mirror onto the Ariane too. That's the other thing. It had to, the telescope had to be taken from its bay and loaded onto a truck and trucked over to a barge, and it made its way on a slow boat.
yeah, it did actually, from California all around South America. I think it's too big to go through the Panama Canal.
I think that's right.
Yeah.
I didn't remember whether it did or not, but I think you're right.
We got Marty over there. We got a comment from somebody already.
Yeah, somebody, I don't recognize the name, Clyde Smith.
Clyde Smith.
It is actually over 20,000 people involved in the program.
20,000 people.
I
Clyde
appreciate that.
Thank you, Clyde. And if you're a part of that, let us know. Right, what we have behind me is just part of something that we see from, you can see from your backyard, that we call it Eta Canary Nebula, Eta Carina.
Yeah.
Eta Carina, okay.
Yeah.
But I just want to, before we get into the science with Dr. Pearlman here, what we're looking at, they're calling it the cosmic cliffs, okay? And you see mountains and valleys that are actually the edge of a nearby stellar nursery on the northwest corner of the Carina Nebula, which is 7,600 light years away. This light is reaching us from almost 8,000 years ago when it left that region. So-called mountains, some towering 7 light years high. You see there, these peaks and stuff, speckled with glittering young stars in infrared light. The steam that appears to rise from the celestial mountain is actually hot ionized gas and hot dust streaming away from the nebula due to relentless radiation. And objects in the earliest rapid phases of star formation are difficult to capture, but Webb's extreme sensitivity, spatial resolution, and imaging capability can chronicle these exclusive events. Something else, huh?
It is something
to look
else.
At this?
It really is. And I mean, the amazing thing about this image is, so the whole thing that we want to learn about with Webb is cosmic origins, right? And cosmic origins in a million different ways. And here we are looking at a place very much like where the sun was born. Okay, the sun was born in one of these regions 4.5 billion years ago. And each and every star that you see in this image is a star that is either in the process of being born or has just been born. Many of them have planets around them.
Did you hear what he said? Many of them probably have planets around
Oh, absolutely. Absolutely.
7,600 light years away.
That's right. And so this is a place like where the sun was born, right? We want to know what it was like when the sun was born and when the planets were created. Well, this is the kind of place that we want to look. And the amazing thing that you're seeing here is just not only all of the gas, and right, the gas is not only the gas that the stars are being created out of, but it's also the gas that's being excited by their starlight, right? When the stars turned on, the gas that's around it goes from being cold to heating up and being ionized, and then gets blown away. And that is part of what you see as sort of those what looks like steam. And it's not really steam.
Yeah.
I mean, it's really it's filaments of gas that are being blown away by this relentless radiation. And what it does is that it creates winds that are hundreds and even thousands of kilometers per second. And they blow away this material. And in fact, if you look at some of the parts of it, one of the things that you can do is for the bright stars, all of those little curves, you can trace it to which star is carving out that little part of the nebula.
Wow. Just like clearing out by the radiation.
Exactly.
Well, we're going to go back to this Karina image here in a minute there.
Perfect.
But
Okay.
I wanted to set stuff up here because, I mean, this is the wow image of the 5 data points shown this morning by NASA, and I watched it. Marty, did you watch it? This morning, did you watch the NASA thing?
Oh, absolutely.
Well, they had an audio glitch on there.
Oh, I noticed.
And Marty, that made me feel good. I was staying curious because we're always having audio problems on there. And I'm going, the production of that was a little bit, typical NASA. They don't have a lot
yeah.
But, yeah, Marty, they had some audio glitches there that I'm sure the Twitter and Facebook geeks were
they
there.
didn't have as much fun with that one as they did with just all of the delays and stuff last night.
Yeah.
Yeah.
When our president showcased a couple of the images there.
That's exactly right. And to be honest, I'm actually glad he did so. I wish he would have let the images speak more for themselves last night, but
he's a politician.
He's a politician, right?
Right.
And so and fine.
Good for them. It was awesome to have have our leader of our country.
He was going to do that. That's exactly right. Yeah.
And it was a good move, and taxpayers' dollars. Dr. Eric Pearlman, we just wanted to shout out to you a little bit about what your expertise is. This is what he knows about.
Right.
These black holes that just let's say in the last 20 years, people like you have increased the knowledge of what's going on here. Most galaxies have black holes. We're going to see a black hole in one of these images.
That's right.
Here in just a minute.
An active black hole, in fact.
Active black hole. And then tell us about this part of your expertise here.
Right. So you are looking at the black hole in the center in each of these images and the disk of material that gets accreted into it. And near a black hole, one of the things that you have is that if you have light that is coming into the black hole, black holes bend space and time. In fact, all mass bends space and time. Okay? And so
we're going to see an example of that here in the deep sky image.
Right. This is the extreme example, and we're going to see a much less extreme example with the galaxy cluster in a little bit. But this is the extreme example of gravitational lensing. And if you look at the upper right, you're looking at the path that light would take in the neighborhood of the black hole. And that is one of the things, one of the many, many things that makes looking at black holes challenging. It's not only that, of course, it's the fact that nothing escapes from the black hole. You know,
so you actually see the debris of stars and stuff going inside as they're heated up. Why have astronomers like you discovered most galaxies have a black hole in the center? Why is that?
So we've discovered that most black galaxies have a black hole in the center in a couple of ways. So first of all, we look at the velocity of the gas and the stars in the center of galaxies. And, you know, what we see is that there is a large unseen mass. Okay. In other words, we know how much mass there should be from the gas and from the stars that's in there. And there's a lot more mass that's there. And you can see it by how fast the material is moving around the center of the galaxy. And this was one of the key projects of the Hubble Space Telescope, was to actually conduct a census of the nearby galaxies and find out how many of the nearby galaxies had black holes. They looked at 35 of them. 32 had central black holes.
So this is a part of the nature of the universe.
That's
and
exactly
the mechanism
right.
behind it, right?
That's exactly right.
And you'll win the Pulitzer Prize of Astrophysics if you can figure that out, my friend, right?
Yeah.
Well, but that's what you're trying to do, right?
Well,
Not
yeah.
win the Pulitzer Prize, but
No. I know what you're saying. I know what you're saying.
Yeah. And with the Webb Telescope, you're one step closer, right?
That's right.
And we're going to see why there. So we're going to see some comparisons here. On the left is an image taken by the Webb, released today. On the right, the Hubble. Comment about what's the difference?
Right. And so this was also the image that was previewed last night
By our president,
that's
Biden, and Nelson, our NASA administrator.
That's right. And so this is a cluster of galaxies with the totally unremarkable name of S-Max 0723. But anyway,
look how clear it is.
It's amazingly clear, and it's incredibly deep. Is it possible to zoom in on some of those? I mean, I know you've got a mosaic
here,
later.
Yeah, we can't do that here.
Okay.
But that brings up a good point, Eric, for you at home to download these pictures.
That's absolutely right.
As high a res as you want. They even have TIFFs available, and you're not going to believe what you're seeing. Everything in this image except the star in our galaxy that's got the snowflake crosshairs on it is a distant galaxy.
That's exact. Well, distant galaxies and you can even see clusters of stars in individual galaxies.
Wow.
That is another thing. So and hold on, step back here because you know, the other thing that you notice here, so you wanted to compare Webb to Hubble. Okay, two things jump out. First of all, it's so much clearer, right? And there's just so many more things. So this is several times deeper than Hubble did, and Webb did this in much less time. Okay, so Hubble took close to 2 weeks to come up with this set of images on the right.
Okay.
Webb did it in 12 hours.
Wow.
So that is the other thing. Whereas, you know, with Hubble, an image like this would be a few times a year. We're just going to keep on pumping these out with Webb. And the other thing is that if you look at all of these arcs, so if you zoom in on this, and we're going to look at this more.
We're going to look at it. We're going at the end here. We're going to.
That's right. We're going to look.
Arcs.
We're going to look at this more in detail later. But if you zoom in on the center, there are thousands of these lensed arcs. We knew they were there. We didn't know how many of them there are many, many times more in the Webb image than they were in the Hubble image. And it's a different band. It's in the infrared, which means that these are more distant objects.
Wow. And this was predicted by Einstein 100 years ago.
Yes.
That gravity, the foreground, would distort light and let the light go around the sides. And that's what the arcs we're going to see. And we'll see some examples of that.
Exactly.
Here's another Spitzer. Did you work on the Spitzer?
So I worked on data from the Spitzer.
Okay.
I did not work on the Spitzer.
One of our great observatories. Spitzer was in the... what wavelengths was it?
That was
infrared.
That was in the mid infrared.
So here's the two comparisons of a Spitzer's best image and the Webb. And
this is an early image, right? This was one of those test images.
Right, yeah, testing the optics.
That's right.
And they didn't want to build the next generation telescope, this was called initially, something that was just 10 times better than the Hubble.
Right.
They wanted it 100 times better, and boy, have they delivered. And here's what we're going to see. Here's the Stephan's Quintet Hubble image and the Carina Nebula again that we were talking about. That this is the entire Carina Nebula, best viewed in the southern hemisphere. This is just a piece of it behind here.
Right.
All right. And so Stephan's Quintet, as an amateur astronomer that I've been 50 years in backyards, this is what it looks like in a backyard telescope, where you can just barely see that there's 5 different elliptical galaxies interacting there. And then, of course, the Hubble, a bigger telescope, would show you more. And then here is the image that was taken by Webb. All right. And we've got 2 different versions, 3 versions of it, there and there. And then this is a different wavelength, and we'll have you explain that in a minute. But what are we seeing here?
Well, let's start a little bit back. Let's start there.
Yeah, there.
Perfect. Yeah. Okay. So what we're looking at here. So yeah, these are the 5 galaxies, and by the way, 4 of them, not 5 of them, are actually interacting, because the one galaxy up in the upper left is actually in the foreground.
Okay, closer to us.
So there's a little bit of cosmic hide and seek going on here. But the other 4 galaxies,
2 in the middle, they're intertwining, huh?
That's exactly right. That's exactly right. And in fact, it's 2 and possibly the remnants of the 3rd that's over to the right of it. That may have been the remnants of a 3rd. Right. And then the one above it. And then the one down at the bottom. That group of galaxies, they are all interacting. They're colliding with each other, and they're forming stars at a ferocious rate. That's another thing that goes on. And one of the things that you're looking at, so if we look at that image, and this is a composite of both the near infrared and the mid infrared images, a lot of what you're seeing is you are seeing star clusters, individual star clusters. Each one of those star clusters is like one of these Carina Nebulae. So if you look at all of these dots, like in the pair of galaxies in the middle, all of those regions,
the string of pearls,
right? Every one of them is a Carina Nebula.
Wow!
And we're looking at hundreds and hundreds of them in that pair of galaxies alone. And this is one of the things that happens when galaxies collide. You would turn a galaxy like our own, which is forming stars, but it's forming like one new star every year. And so it's not forming stars at anything near the rate of these galaxies here. These galaxies here are forming stars at 200, 300, 400, 500 times the rate of our galaxy,
because the gases are interacting, and
exactly.
That's how things are. And so this is two key words: mid-infrared and near-infrared.
That's exactly
And
right.
so this is the one, and this is the other one. Look how the difference.
Right. So we first looked at the near infrared, and now we're looking at the mid infrared. And they're showing us different things. So the near infrared, let's go back to that. The near infrared is showing us mostly starlight from old stars, and it's not concentrating as much on the warm gas.
You don't see any of the red or those little pearl-like looking zones.
Exactly. I mean, the reason why you see in the mid-infrared that string of pearls, all of those regions where stars are forming, is because those are regions where the gas is much denser and it's colder.
Mm-hmm.
And so you see the light from those in the mid-infrared. And one of the other things that you can see more and more of as you go from the near infrared to the mid infrared is that, so there's dust in all of these regions, right? And you can see it also in the Carina Nebula there, right? There is a lot of dust there. And if you look at the Carina Nebula, if you look at those cliffs, right? All of these places where it looks dark, it's not dark, right? It is dark, or it appears dark, because there is dust there, and that dust is blocking out the light of the stars behind. Okay, and so if you go back to the Stephan's Quintet images, go ahead.
Infrared, though, it can see through some of that.
That's exactly right. And as you go to longer and longer wavelengths, you see through more and more of the dust. Right.
Now, what turns you on is probably those bright nebula nucleus there. I mean, it's not nebula.
That was the big surprise for me. That's exactly right. Because
look at the brightness there in the near infrared.
That's right. We did not expect that one of these galaxies had an active black hole, but there it is. So the one at the top.
One at the top, real bright.
That's right.
And it has already done the analytical data like you all do.
That's exactly right.
Composition.
That's right. And so what you're looking at here is you're looking at a composite image. So you got the image on the left, and then we're going to zoom up on the upper galaxy, right? And so that is the galaxy that has the active black hole. And then what was done is that spectra were taken, first of the nucleus, and so the nuclear spectrum is the one on the bottom, and then looks like they also took a spectrum of a region off to the side, and so that is the spectrum up at the top, and they're different, right? That's one of the things that you notice. And if you take a look at the spectrum of the nucleus, not only do you see lots of features from dust, right? Those are those silicates, but you see really bright emission lines, and you also see a lot of other stuff, that big infrared bump, and the combination of those two things plus the very bright nuclear source, that means that there is an active nucleus there. And so that was a very big surprise. It's an amazing surprise for somebody like me, because I didn't think that would be there
already. And there was they said in the press conference today that there'd be a 5 to 7 day cycle every week where new data like this, like you said, the Hubble was taking a couple weeks to gather data, where they're gonna be dumping new data and stuff going on,
and probably every 5 to 7 day cycle is going to be bringing us several more of these, because there's a few hundred different observations that are set to happen this year, right? And each one of those, some of those take a very long time, but some of them are very short, right? So each 5 to 7 day cycle is probably going to contain 10 or more of these observations, depending a little bit on what the schedule is each week.
Well, you told me you've got some time reserved on the web. When's your cue
Actually,
come up?
I don't know where you got that from because I
Oh.
don't this year.
Oh, you don't this year?
I
Okay.
tried, but I didn't get.
Okay. I thought you said you had a couple of years out.
No,
on something.
I have colleagues who do, but I don't.
Well, how's that determined?
Right. So what happens is that it's a very competitive process. Every year, the Space Telescope Science Institute issues a solicitation for proposals, and it's a big deal in the astronomical community. They typically get about 2,000 proposals every year, sometimes more than that. And in any given year, they also get several times more proposals than they have time to do. Typically 5 to 10. I think this first year was like 12 times as much as they had time to do. The competition is incredibly keen, incredibly tough, right? And so, you win time on the web. Your proposal is one of the best, and you got a little lucky. That's the other thing too, right? Because when you do a selection process like this, and I've done it many times. I didn't participate in the first one for Webb, but I've done it 5 different times for Hubble, 3 or 4 different times for Chandra, and so on. Every time you get more really good proposals than you have time to award. But you've got to pick some, right? You've got to pick the ones that you think are the best. But that always means that you leave a few, more than a few, that are really worthy on the side for the next year. And so that's the process, right? You start out with about 2,000 proposals each year, and the teams of astronomers that the Space Telescope Science Institute assembles, and they usually assemble 10 to 12 different teams of astronomers in different subject areas. Their job is to narrow those 1,500, 2,000, possibly more, down to however much time the Webb has to give in a given year. And like I said, it's generally around 300 observations in a year.
Well, we hope you get on one of those one day.
Fingers
there.
crossed.
Fingers crossed on that. We're going to go through the other images that were shown. There, of course, is the Carina Nebula. There, beautiful. This is what it looks like in a backyard low-power telescope. It's almost like using binoculars on it in your backyard. It's in the Milky Way. That's why you got all those stars in the background there.
That's right.
But one of the things that we've looked at the birth of stars behind us here, so it was natural that they would showcase an object that had the death of stars, and that would be the Ring Nebula, the Southern Ring Nebula. There's one in the northern that looks like a little smoke ring, and one in the south, and there it is through a backyard telescope, basically, and here it is through Whoa,
you've got both images there.
Yeah, of the Webb and the ring, and the other one's what? Oh, that's the below it is the exoplanet we're going to see here in a second.
No, that's actually that's SMAX 0723, the cluster.
Oh, right. Okay. Right.
Yeah.
Okay.
Yeah.
But here is a star that exploded, and there was a surprise in this image.
There's a few surprises actually. So let me go let me go one by one through the different surprises. I actually want to start with not the center of the image, but the structure that you see. Okay, so when you look at this from the ground, and even when Hubble looks at this, Hubble does not see this incredibly intricate structure in that ring nebula, okay? And what am I talking about? If you look at that, you don't see one ring, right? There is that bright ring, but there are actually several different rings, okay? So this material that was thrown out by the star that died, it was thrown out in several different episodes, right? Each of those shells is an episode where the star lost mass.
Okay.
And, this is a history of how the star lost mass. The star didn't just explode, it lost mass over thousands, probably tens of thousands of years.
Burping it off, so to speak.
Burping it off every once in a while. Each of those shells represents one of its active phases where it was throwing off a lot of material.
Mhm.
And this is looking at a time history. And, if you think about it, so geologists like to think about gathering core samples,
Mm-hmm.
okay? And I think this is a great analogy for what's going on, because you're looking at a time history here, right? A core sample is a time history of what happened to that particular area of, that continent at a given time, right? If you look at the rings, the layers in the Grand Canyon, right? Each layer comes from a specific time period. And so by going down the Grand Canyon, you're looking at a time history. So here you are looking at the history of the material that was thrown off of this star. And the surprise, the first surprise, it's not the only surprise, the first surprise is that it was thrown off in shells, right? So there was an episode of, and it wasn't just a burp, it was probably many burps over, many years. And then it went quiet for a while.
Mm-hmm.
And then it started to throw off more mass. And then it went quiet for a while. And then it threw off more mass. Each of these, right, the bright ring is the final episode. But then as you go further and further out, you see episodes that occurred longer and longer and longer ago. It's just amazing.
I understand this is a fate that will befall our own sun, right?
That's exactly right.
Here's the other image,
that's
two
right.
images of it there.
And I think it's great that you put it up, because I think this illustrates another one of the surprises that was in here. So you're looking at the near-infrared image, near-infrared and mid-infrared image on the left
Webb.
and right.
Mhm.
It's the near-infrared image
But
that
there's
you're looking.
two stars on the right.
That's where I'm getting to, right?
Yeah.
The mid-infrared image on the right, you see two stars on there. Now, we knew that there were two stars. We knew that they were there. And the reason we knew that they were there is because this isn't a circular nebula, okay? So if you compare this to the ring nebula in Lyra, right, the northern ring nebula, the northern ring nebula in Lyra is almost a perfect circle, right? Well, this isn't. This is not a perfect circle. This is egg-shaped. And the reason that it's egg-shaped is because it's a double star, right? And so if you have a double star, then the star that's dying is orbiting its companion.
Mhm.
And as it orbits its companion, it throws off material in different ways.
Wow.
And so because of the shape of the nebula, and also because of some spectroscopy that had been done, we knew that this was a double star, but we'd never seen the other star. And so the beautiful little surprise that was hidden in the center of this image, there it is. There it is.
They also talked about a little surprise. There's a galaxy.
Yeah,
hidden
and
in
that's
there.
and that's a cosmic coincidence, right?
Yeah.
So for those of you looking, this is what looks like a little streak off to the upper left.
About 10 o'clock.
About 10
Yeah.
o'clock. That's
There.
exactly right. And to the eye, it looks like something that might be associated with the nebula. And they had to investigate. There we go. That's exactly what we're talking about.
Marty.
Thank you, Marty. So, yeah, they talked about that this morning. there was actually a bet going on apparently among the different people because it was not at all clear what that was. What people thought that was
maybe light shaft type of thing, right?
It could have been. It could have been light that got reflected by some gas that was further out. But if you look at it closely, and then if you take a spectrum, that turns out to be an edge-on spiral galaxy that just happens to be there, and just happens to be aligned in such a way that it points directly back at the center of the nebula where the two stars are. It's an amazing coincidence.
Yeah, a lot of juxtaposition there.
Yeah.
Well, one of the other announcements was not of an image, but of data, and this is your data, or someone's that you sent me, and we can go back to that. But they compared the atmosphere of a nearby exoplanet orbiting another star, no images taken. The data of the infrared images found a lot of water vapor in the atmosphere. This
is incredibly exciting. So let's look at this. This was a spectrum taken with Hubble, and we knew there were clouds, right? And the reason we knew that there were clouds
on this planet orbiting another star.
On this planet is because what we saw were these lines in the spectra. And these lines, the way that you gather spectra like this is that this was taken when the planet was in front of the star. This is a transiting planet, okay? And so you take a spectrum when the planet is in front of the star. And what you're taking advantage of is the fact that the light from the star has to go through the atmosphere of the planet.
Mm-hmm. I'll show this slide there.
Exactly, right. So you're taking a spectrum at various times there, and you take advantage of the fact that the light of the star goes through the planet's atmosphere. And then what you do is you look for lines in the spectra. They tell you what the atmosphere is made of, and then they can also tell you whether it is just a smooth distribution like a haze, or whether there are clouds. And so if we go back to the previous spectrum, that one, yes. So that showed us that there was sodium and potassium in that spectrum. And if you look, one of the other things that it showed us is that there did happen to be a deck of clouds. So you wonder, what's in that deck of clouds? And that deck of clouds, before we shift to the next image, it's at 1,000 degrees, right? So it should be way too hot for there to be a lot of water. Now we go to the next image, and yeah, there's a lot of water there. And this is water at 1,000 degrees, right? So it is water vapor.
Steam.
It's steam, right? And because it's at 1,000 degrees, that also means it's under pretty high pressure, right? Because to get water vapor in this amount, at 1,000 degrees, you usually do need high pressure. The other thing that's really interesting there is, so first of all, usually when there's water, there's life, right? We didn't think that there would be that much water there. There is. Now, we think that it's probably hard for life to form, but we have one example right now, right? We have the Earth. Could we be wrong? Oh, yes, we could be wrong. Let me silence my phone. I don't know what's going on here. We could definitely be wrong. And that's the exciting thing, right? We could be very wrong, and we could be looking at a place that we hadn't thought of where life forms. Now, this may be too extreme, but we don't know. We don't know.
No, we don't. Well, you're just a popular guy, Dr. Pearlman. Everybody wanting to know your insight here, and we're
I
so
guess,
glad that
I
you're
don't
with
know.
us on Stay Curious today. Marty's got a list of all you out there that are watching today, and we just got one more of the images to cover. We're so glad that everybody's with us today. We got mentioned Keith Soul. He's teaches astronomy at the other college, Florida. What's the name of it, Marty? Forgot.
Florida East Coast.
Yeah, Florida
East Coast.
East Coast. Florida East Coast. Keith, I'm sorry. He's an astronomy professor. He's digging this. We got Bryneth watching. Melissa Pope. Hope you're working hard to Space Coast Office of Tourism. Hey, Tom Musiak. We got your pictures of the shuttle we'll be posting. Ricardo Gonclaves is watching. Dave Stange is one of our big watchers up in Michigan.
Mm-hmm.
Adrian Padrick, that's a new name. Clyde Smith. Madeline Vanderland. Anybody you know on there? Michael Haddad is our payloads guy. Hey,
Okay.
Mikey. Good to see you, buddy. Lauschma is watching. Roger Clinchman. Gary Gerald. And Ben Husett. We're so glad that everybody's enjoying this conversation. 20 viewers on here today. Quite popular, of course, getting our fill of the Webb images today. And we're going to segue from that to the deep space image that was making a lot of... we're going to end with this. There's several little areas we want Dr. Pearlman to comment on here because this is a time machine, Dr. Pearlman.
It sure is. This is a time machine.
And
Absolutely.
we're looking back at the... how old do we say the universe is? Basically?
So we believe that the universe is about 13.8 billion years old.
13.8 billion. And there's a galaxy in there that's 13 billion light years away.
That's exactly right. And
so what are we looking at here? Tell us that, and then we'll go to these other images.
So we are looking at the cluster of galaxies, right? And the cluster of galaxies is not what's 13 billion years, what's 13 billion light years away, right?
Yeah,
the cluster of galaxies
is
about 4.5 billion light years away. But it represents a very large amount of mass, right? And I mentioned that mass lenses light, right? It gravitationally lenses light. And we're looking at a whole bunch of that because one of the amazing things that you see, and we're gonna zoom up on that in just a minute, is that you see hundreds and hundreds, probably thousands of these lens arcs.
We'll go back to that here while we're there.
Yeah,
close up your lens.
That's
arc.
a close up, and there's some of them. Yes, yeah. And you can see several of these. These are close ups on a number of the galaxies, and I think the most amazing one that you can see is that one above the bright galaxy in the upper right.
Yeah, like 1 o'clock there, Marty.
About 1 o'clock. That's hex, exactly right. Yeah.
Where you see the crosshairs are actually an artifact of the secondary mirror.
Yeah, a little bit. No, further over to the left. Yeah,
a little left. There
it is. Perfect.
Yes. That one looks like. Let's see. It looks like that one on the left center there.
That's exactly right. And if we just put that up, there's actually two of these arcs to look at there. So the first one is the bright one that we were looking at. And that looks sort of like a tadpole. That is a bright galaxy that was gravitationally lensed, most likely, actually, not by the cluster itself, but by the bright galaxy that happens to be at the lower left in that particular cutout. But then the other thing that's amazing about that is that string of pearls that you see stretching across the upper right hand of that cutout. And that is another galaxy. But what's amazing about that is you're only seeing what look like individual star clusters in that. And that's the amazing thing. You're not just looking at galaxies here. You're looking at star clusters in those galaxies. There is a level of detail here that is just incredible.
Sure
So this is one of those images. And by the way, this is not the only one, right? This one, the Carina Nebula, what you want to do with those images, if you're looking at these, don't take 5 minutes. Take 30 minutes for yourself and pan across it, zoom up over here, zoom up over there, zoom up on a million different things. I don't care what you zoom up on, right? There is a ton of detail in this image that you can zoom up on, and every one is so interesting.
Mm-hmm.
And so, yeah.
Here a few of them are isolated,
Yep.
and at the bottom it's pointing to what you're looking at in this image, and the bottom one is 13 billion light years away.
That's right. That's right. We're seeing the light emitted 13 billion years ago from that. And so just to put it in perspective, one of the things that we want to find with Webb is we want to find the very first stars, the very first galaxies. We want to find the galaxies and the stars when they turn on. We are looking at some of those very first stars and galaxies here.
It's amazing looking at creation, basically. Marty, what's the comment there?
Comes from Clyde Smith, and it's a compliment. You always have very good and interesting shows, but today is the best ever. You've done a far better job than NASA Goddard did today. Great guest, and you always work.
Thank you. I
Who said
appreciate that.
Clyde Smith.
I appreciate that.
Yeah, there was a lot of production value to today's NASA thing instead of science, and I don't know. It was very interesting in there. Thank you very much, Clyde.
It was.
We try hard here. This is, I think, our 610th episode of Stay Curious, since Marty and I have been doing this. Started in March 2020 out of the pandemic, and you have been a great guest, as usual, dissecting this complicated stuff down to where we can understand it. And here's a final look at your gravitational lensing.
Right.
And what you're talking about is these galaxies you're seeing are actually behind this cluster, and gravity is moving it around. You're the expert at that. That's what we showed in the beginning.
That's right.
Black holes will also do that and show things that are behind. It's like looking eyes in the back of your head. Are you seeing there?
And if you were to take a glass, and this water bottle is not a great thing, but if you were to look at a light bulb through this, and you can sort of see that through here, one of the things that you can see is that the light from that light over here is actually broken up into rings.
Right. Yeah. Right. Good analogy.
And so that's the bottle here is serving as a lens.
Bottle. Yeah.
Or yours. Sure.
If I'm pointing
exactly.
that,
right.
you actually see light around the edge, or even pointing it towards you there.
That's right.
That's what's going on there. That is an excellent analogy.
That's
there.
right. And so here you have the cluster of galaxies and the mass in the cluster of galaxies serving as your lens. And by the way, it's not only the cluster, right? We also see individual galaxies serve as a lens. But so light from galaxies gets broken up into little ringlets, right?
Mm-hmm.
And ideally, you'd want to see a complete ringlet. But that you only see if the alignment is absolutely perfect, right? And usually the alignment is not quite perfect. So what do you see then? What you see then is partial rings, but of the same galaxy littered around all over the place, right? And so you should be seeing several images of the same galaxy at the same radius littered around. And so if you go back to that spectrum, one before.
There we go.
There it is. Right. So let's go back to that and zoom up on that. Right. Those two ringlets are the same galaxy. And the way that we know that they are the same galaxy is by looking at the spectrum.
The data you have on the
That's
right.
That's the data that you have on the right. And if you notice, the spectra are identical. And that is the key thing, right? Spectra are a fingerprint.
Good. As I was going to say, yeah, that it's everything emits a energy wavelength, and that is your fingerprint.
That's exactly right.
And so they know no two are alike, and that's how we understand a lot of things without seeing them.
Yep.
So, Dr. Eric Pearlman, you have been fabulous as usual. Marty, we got any other housekeeping there?
No, just 2 more watchers.
Okay, we've got
Lisa Marie
and
Cynthia Rossi.
Hey, Cynthia. She's a big fan of Stay Curious, and now she'll be a big fan of Dr. Eric Pearlman.
Well, thank you.
On there. So, Dr. Pearlman, we have to end our show with, who in the heck was James Webb? All right, and I teased you a little bit there. Nobody talked about this great man today. Shame on you, Bill Nelson, for not mentioning the greatest NASA administrator we ever had, James Webb. This was going to be called the New Generation Telescope. Mr. James Webb died in 1992 at age 85, so he has no idea, of course, that this was going to be named after him. He was NASA's administrator from 1961 to 1968. The first administrator was, I knew who it was, Eric. Anyway, he was the second NASA administrator during Mercury, Gemini, and Apollo.
Mm-hmm.
Here he is shown with the lunar module, Marty, of your Grumman engineers there. That is the 1962 version of it with the round hatch to exit from. And that's the lunar module, lunar orbiter, that very important for those orbited the moon to plan the landing sites with the geographical maps that they made there. So that is who Mr. James Webb is, and he just the Hubble telescope, named after the great astronomer Edwin Hubble, who was also a boxer. You knew that, didn't you?
Yes, I did. Yes, I did.
Yeah, Marty.
Tom Glennon, first administrator.
Tom Glennon. Thank you very Glennon, the first NASA administrator. Thank you, Marty. But that is what the Webb telescope was named after. This man who was more of a politician, of course, and an engineer to get the $40 billion to go to the moon in the 60s. So, and here is his telescope. And Dr. Pearlman, we really appreciate you keeping our throngs of people staying curious on here. We hope, and I'll send you the YouTube link because we've monetized YouTube since you were here in January, and we're sure that we'll have a lot of visitors to our YouTube site as well as our Facebook where we got started. Is there anything you'd like to comment about?
No, not really.
Esoterically or anything here? You've been a busy guy today. Look at this gorgeous cosmic reef.
I know, it's amazing. Again. I mean, so I want to kind of comment on two things to go out.
Take us out.
So first of all, I'm a kid in a candy store right now, and my candy store is the entire universe. And this is what is amazing, right? I'm going to be unwrapping present after present, and each one is just going to be incredible, right? So that's the first thing. The second thing is just a reminder to everybody. We forget, we've gotten spoiled with things being fantastic. Things like this only happen when you dream big. And so the Webb Space Telescope, the James Webb Space Telescope, is a great example of what happens when you dream big, right? This was a 30-year journey that started with, okay, what comes next after Hubble? And the idea was to build something that was several times Hubble's size and much more sensitive. But that took an enormous team spanning several countries, partnerships between NASA and ESA and the CSA and many different companies, and 30 years. And it was almost killed several times.
Mm-hmm, sure was.
This is the culmination of this magnificent dream, this magnificent idea, and you only get this when you dream big and when you think big. And so what I want to communicate to the people listening today is that NASA and space, this is not just a mundane undertaking, right? No, we are thinking big. We are thinking about exploring the moon, exploring Mars, here exploring the very earliest episodes of the universe. And you can only do this if you have these big thoughts and big dreams. And here's the result. I mean,
what a time to be alive!
What a time to be alive!
Astronomer,
Yeah, absolutely.
For sure. I was holding out just to see Pluto 5 years ago. Marty, what have you got, my
I
friend?
got two questions. I'm going to ask them both at the same time.
Okay.
You want to comment on your tie and what comes next after Webb?
So this tie actually is an artist's impression of gravitational wave signals. And I'm wearing it today. I'm a black hole guy.
Gravitational waves, another
That's right.
outgrowth of black hole. Okay.
And by the way, that is one of the things that the last 5 years has really shown us. This is an amazing time to be alive as an astronomer, because the last 5 years we have seen observing with gravitational waves go from somebody's notion, somebody's dream, to a reality, right? LIGO.
Yeah.
And the results from LIGO already won a Nobel Prize. There's 2 more coming from LIGO, which are in the hopper. They're going to win Nobel Prizes. The merging neutron stars and the neutron star black hole pairs, these are things that are going to win Nobel Prizes. So that is what this is about. And I just thought, because this morning I was getting ready for all my interviews and all my appearances, including this podcast. But I said, okay, what is the best tie to wear?
Yeah.
And this is what I picked.
Cool. So Marty asked, what's after Webb?
What's after Webb? I would love to know what's after. So what I do know that's coming next, the next 3 observatories. So every 10 years, NASA goes through a decadal survey, and there were 3 telescopes that were recommended. One is an ultraviolet telescope. Another one is an infrared telescope, and then the third one is a X-ray telescope. So each one of these is supposed to be a big improvement on the previous generation of space telescopes that came. I mean, so that is what is next. Each one of these, by the way, is going to be a generational project, right? Webb was a generational project because it took 30 years from when it was first streamed up. It was first streamed up in the early 1990s. I was at the Space Telescope Science Institute between 96 and 99, and so I saw some of those early discussions. And each one of these 3 telescopes is going to be a generational undertaking, and it's going to be each one of them is going to be an immense improvement on the telescopes that come before. So these are the next 3 big missions in astronomy. Now, there's going to be many smaller missions in between, but those 3 missions that were approved by the Decadal Survey, those are the next 3 that NASA is looking at. And there's going to be, again, probably a 30-year effort to put them in space. Each time you put something this size into space, it is a multi-generational effort. Hubble was a multi-generational effort, and Webb was a multi-generational effort, and Chandra was a multi-generational effort. So will this.
Incredible. Dr. Pearlman, thank you. Just think, 100 years ago, Edwin Hubble was writing papers convincing people with the 100-inch Hooker telescope on Mount Wilson, the largest telescope of the time in 1915, 1920. They didn't even know that the Milky Way they thought the Milky Way was the whole universe.
That's right.
And Hubble said, no, the Milky Way is one island of galaxies, of stars, and there's thousands and hundreds of thousands, he thought, of galaxies. Today, you have seen the near galaxies at the precipice of the birth of the universe.
Absolutely. Absolutely.
In 100 years, we've come that far.
That's right. And this is what's so exciting about being an astronomer, is that you're seeing all this happen, these discoveries, and it's in real time. I mean, it's just amazing.
Well, the best is yet to come, because this is just a taste of what the Webb will do. We look forward to having you back many times, Dr. Pearlman. An outgoing comment, Marty?
Yeah, from Lisa Marie. Thanks, Dr. Pearlman, for inspiring my team to dream big, really big.
All right. Thank you, Lisa
appreciate
Marie.
that.
All right. And with that, that's a good way to go out, because we're always dreaming big here on Stay Curious. And we've got a big dreamer tomorrow on our show, Mr. Terry White, who was a manager of one of the shuttle orbital processing facilities.
Oh, fantastic.
He is going to be doing a monthly program, the Shuttle Garage with Terry White. So we will kick that off tomorrow on Stay Curious. I thank Dr. Pearlman again for your graciousness to come here today, about an hour drive from Melbourne. And Marty, thank you for a flawless show today. We finally had a good show where everything fell into place, and our audio was a lot better than NASA TV had today.
You know, the worst was that pre-theme music last night.
Okay.
I'm sorry, that was horrible.
All right. Should have been a patriotic.
I know.
In the background. All right. Well, thank you everybody for Stay Curious. I'm Mark Marquette, and we will see you again tomorrow to bridge the space between us.